approximately 68% of the total energy content of the universe. We have no satisfactory physical explanation for what it is. A dead star reaching its limit and exploding told us that dark energy exists. This is not speculation. This is what the data says. The discovery won the Nobel Prize in Physics in 2011. Stars with masses greater than roughly 8 solar masses do not stop at helium burning. The mass is sufficient to generate the gravitational pressure needed to heat the core beyond the helium burning threshold, igniting successive rounds of fusion with heavier and heavier elements. Carbon burning, neon burning, oxygen burning, silicon burning. Each stage produces heavier elements from the ashes of the previous stage. Each stage generates less energy per unit mass than the one before it. Each stage lasts a dramatically shorter time than the one before it. A massive star spends millions of years burning hydrogen. It spends hundreds of thousands of years burning helium. Carbon burning lasts approximately 1,000 years. Neon burning lasts roughly a year. Oxygen burning takes months. Silicon burning, the final stage, takes approximately 1 day. 1 day. The final stage of a massive star's nuclear burning, the last thing the star's core does before it ends, lasts approximately 24 hours. During those 24 hours, nothing on the surface of the star looks unusual. The star is enormous, red, and bloated in its outer layers. From any distance, it appears as it has for thousands of years. The surface shows nothing, no trembling, no brightening, no change in color. Inside, at the core, everything is ending. Silicon burning produces iron, and iron is where fusion stops. The reason is fundamental to nuclear physics. The energy released by nuclear fusion comes from the fact that the products of fusion have slightly less mass than the inputs. That mass deficit becomes energy. But this only works when you're fusing elements that are lighter than iron, because iron nuclei are the most tightly bound nuclei in nature. The nuclear binding energy curve, a graph that shows how tightly bound nuclear matter is at each atomic number, reaches its minimum at iron. Fusing elements lighter than iron moves you toward this minimum, releasing energy. Fusing elements heavier than iron would move you away from the minimum. The reaction would consume energy rather than release it. The star cannot run on iron. Iron is the end of the road. The nuclear burning stops. And when it stops, the balance between gravity and pressure that has held the star together for millions of years collapses in an instant. The iron core that has built up in the center of the star, a sphere roughly the size of the Earth, containing roughly 1.3 to 1.5 times the mass of the Sun, loses its pressure support in a fraction of a second. There is no more outward push from nuclear burning. Gravity takes over completely. What happens next takes place in approximately half a second. The iron core collapses inward at roughly a quarter of the speed of light. This is not a slow collapse. This is not a gradual shrinking. In a fraction of a second, an object the size of the Earth has compressed to a sphere roughly 20 kilometers in diameter. In less time than it takes to blink, an object the size of the Earth becomes an object the size of a city. The density at the center reaches nuclear density, the same density as the nucleus of an atom, which is ordinarily and almost inconceivably small and concentrated object, and which is now being achieved by something with a mass exceeding the Sun. At this density, electrons and protons are forced together by gravity to form neutrons, releasing an enormous flood of neutrinos. The neutron-rich material at the core reaches such extreme density that it can no longer be compressed further. The neutrons themselves resist further compression via quantum mechanical effects, specifically neutron degeneracy pressure, and the strong nuclear force that holds atomic nuclei together, which now operates at the scale of the entire core. The inner core becomes rigid. The outer layers of the iron core, still moving inward at a quarter of the speed of light, slam into this suddenly rigid inner core and bounce. The bounce sends a shockwave exploding outward through the star. The shockwave alone is not sufficient to blow up the star. This is a critical point, and it took decades of increasingly detailed computer simulations to fully understand. The shockwave stalls. It loses energy fighting its way through the dense overlying material, and it would eventually die out, leaving the star to collapse silently into a black hole. What revives the stalled shockwave is the neutrinos. The collapse of the core has released approximately 3 × 10⁻46 joules of energy in the form of neutrinos. To make that number mean something, this is more energy than the Sun will radiate across its entire 10 billion year lifetime, released in approximately 10 seconds. It is roughly 100 times more energy than would be required to completely disrupt the star. Most of this energy is in the form of neutrinos, which are ghostly particles that barely interact with ordinary matter at all. Under normal circumstances, a neutrino could pass through a light year of solid lead without interacting with anything. That is not an exaggeration. That is what the experiments show. But the material around the collapsing core is not ordinary matter at ordinary density. It is matter compressed to densities found nowhere else in the observable universe except inside the cores of collapsing stars. And even the weakly interacting neutrinos, passing through matter at this density, deposit a small fraction of their energy into it, perhaps a few percent. That small fraction is enough. The deposited energy heats the matter behind the stalled shockwave. The heated matter expands. The shockwave is revived. It accelerates outward. Within hours, it reaches the surface of the star. The star explodes. This is a core collapse supernova. The explosion releases roughly 10⁻44 joules of kinetic energy in the expanding debris. For a period of weeks, the supernova can outshine its entire host galaxy, outshine 100 billion other stars simultaneously. It is visible across cosmic distances. The supernova observed by Chinese astronomers in 1054 CE, which they recorded as a new star bright enough to see in daylight for 23 days, was a core collapse supernova. The remains of the star it destroyed are visible today as the Crab Nebula, a cloud of expanding gas and tangled magnetic field 6,500 light-years away and roughly 11 light-years across, still expanding at approximately 1,500 kilometers per second, almost 1,000 years after the explosion. At the center of the Crab Nebula, visible in X-ray and radio observations, is a pulsar rotating 30.2 times per second, the directly observable corpse of the star that died in 1054. The Chinese astronomers who recorded its birth and the astronomers pointing modern telescopes at its remains are connected across 10 centuries by the same physical object. During the explosion, in the extreme conditions of the shockwave moving through the star's outer layers, temperatures and densities found nowhere else in the present universe, fusion happens. Elements heavier than iron are forged. The rapid neutron capture process, which astronomers call the R process, assembles atomic nuclei faster than they can decay, stacking neutrons onto existing nuclei to build elements that would otherwise be impossible to create. Nickel, copper, zinc, selenium, strontium, silver, tin, iodine, barium, gold, platinum, uranium. The periodic table of elements heavier than iron was written, entry by entry, in the hearts of exploding stars. This is not a metaphor. This is the actual physical mechanism. Spectroscopic analysis of supernova remnants confirms the elemental composition. Multiple independent measurements, multiple independent teams. This is established. The aftermath of a supernova is itself a remarkable structure. The ejected material, moving outward at thousands of kilometers per second, sweeps up the surrounding interstellar gas. The leading edge of this expanding bubble compresses and heats the gas it encounters, producing a shockwave visible at radio, optical, and X-ray wavelengths. Electrons in the magnetic field of the remnant are accelerated to nearly the speed of light, emitting synchrotron radiation, a ghostly blue glow, invisible light, caused entirely by relativistic electrons spiraling around magnetic field lines. The entire structure expands over thousands of years, eventually slowing as it sweeps up more and more interstellar material until it merges with the surrounding gas, and its identity as a supernova remnant is lost. The Cassiopeia. A supernova remnant, the remains of a massive star that exploded approximately 340 years ago, whose light reached Earth sometime around 1680, but was apparently not noticed or recorded at the time, is one of the brightest radio sources in the sky outside the solar system. It is 10,000 light-years away and roughly 10 light-years across. The James Webb Space Telescope has imaged it in unprecedented detail, revealing the distribution of elements within the ejecta, where the iron is, where the silicon is, where the oxygen is, mapped across the physical structure of the remnant. The chemical fingerprint of the explosion, preserved in the expanding gas, is readable 340 years after the fact. The star's interior, which was inaccessible to any observer while it was alive, is now laid out across 10 light-years of space, where we can read it. The iron in your blood was made in a core collapse supernova. The gold in any ring you might be wearing was made there too. The iodine that your thyroid uses to regulate your metabolism. The zinc that supports your immune system. The calcium in your teeth. All of it forged in the death of stars, scattered into space, mixed with clouds of gas and dust, gathered by gravity into a solar system, deposited on a planet, and eventually incorporated into you. The formal understanding of how stars synthesize elements was established in a landmark 1957 paper by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, known in the field as B2FH, the initials of its four authors. The paper is titled Synthesis of the Elements in Stars. It is one of the most cited papers in the history of astrophysics, and it laid out, for the first time in a complete and systematic way, the nuclear processes by which stars produce the elements of the periodic table. Hydrogen fusion, helium fusion, carbon, neon, oxygen, silicon burning. The S process, slow neutron capture, which builds elements like barium and strontium in the relatively calm interiors of red giant stars. The R process, rapid neutron capture, which builds the heaviest elements in the violence of supernova and neutron star mergers. The P process, which explains a handful of rare proton-rich isotopes. Every element on the periodic table accounted for, with a stellar process responsible for its creation. This is established. It is peer-reviewed. It has been confirmed and refined by 60 years of subsequent observation and nuclear physics experiments. William Fowler received the Nobel Prize in Physics in 1983 for his contributions to understanding nucleosynthesis. Fred Hoyle, despite contributions to B2FH and despite his prediction of the Hoyle state that was confirmed by experiment, never received a Nobel Prize. Margaret Burbidge, who led much of the observational work and whose contributions were central to the paper, was offered the Annie J. Cannon Award in Astronomy in 1972, an award given only to women, and refused it on the grounds that it was discriminatory by design. She is one of the pivotal figures in our understanding of where the elements came from. The history of the science of stellar death is full of people whose contributions were not fully recognized in their time. You are the recycled material of stellar violence. This is established. This is real. We have direct observational evidence from only one nearby supernova in the modern era, one event close enough and coinciding with instruments sensitive enough to reveal the physics of stellar death as it happened in real time. Supernova 1987. A occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, on February 23, 1987. It was approximately 168,000 light-years away. It was the first naked-eye supernova visible from Earth since the supernova Kepler observed in 1604. The light that reached Earth that night had been travelling through space for 168,000 years. It left its source at a time when our species had been anatomically modern for perhaps 100,000 years at most. There were no cities, no written language, no agriculture. The light crossed the galaxy while our ancestors painted cave walls and invented the bow and arrow. In the hours before the optical explosion was detected by any telescope, neutrino detectors on Earth registered a brief burst of particles, one in Japan called Kamiokande 2, one in Ohio called IMB, one in Russia. 19 neutrinos in total across approximately 12 seconds. 19 particles from 168,000 light-years away. These 19 particles, out of the unimaginably vast flood of neutrinos that had streamed through the planet, were enough to confirm the core collapse model in its essential details. The timing, the energy, the duration, all consistent with what the theory predicted. The light from the explosion arrived at Earth approximately 3 hours after the neutrinos, exactly as the models said it should. The neutrinos left the stellar core as it collapsed, passing through the still intact outer layers of the star before those layers had been touched by the shockwave. The light arrived later because it had to push through those outer layers first. The time difference between the neutrino burst and the optical brightening confirmed, in a single observation, the sequence of events that theorists had described for decades. One supernova, 19 particles, and the entire core collapse picture was validated. The star that exploded was identified in archived photographic plates as a blue supergiant, not a red supergiant, which was the stellar type that most models had predicted should undergo core collapse. This complicated the models and required revision. This is what observational data does. It does not always confirm the model. Sometimes it forces the model to improve. That forcing is how science makes progress. The remnant of supernova 1987A has been studied continuously ever since. The shockwave moving outward through the surrounding gas has been watched in real time as it lit up rings of material expelled by the star in the thousands of years before it died. The expanding debris has been mapped in multiple wavelengths over nearly 4 decades. And yet the neutron star, which should be at the centre of the remnant if the standard model is correct, evaded direct detection for decades, hypothesized to be obscured by the thick cloud of dust surrounding the explosion site. Recent observations with the James Webb Space Telescope have detected infrared signatures consistent with a compact central object in the remnant, something hot enough to warm the surrounding dust from within. The data is being analysed. A neutron star appears to be there, but it has not been unambiguously confirmed and directly imaged. The nearest core collapse supernova remnant from the modern observational era, the event that provided 19 particles to validate decades of theory, still has not given up its final secret. The instruments are improving. The answer will come. When the outer layers of the massive star are blasted away by the supernova explosion, the collapsed inner core remains. What remains is a neutron star. A neutron star is an object so extreme that ordinary intuitions about matter fail entirely before you even reach its surface. The result of the collapse is a sphere composed almost entirely of neutrons, roughly 20 kilometers in diameter, containing between 1.2 and 2.3 times the mass of the Sun. The density of a neutron star is approximately 10 to the power of 17 kilograms per cubic meter. A teaspoon of neutron star material would weigh on the surface of the Earth approximately 10 million tons, not 5 tons as with white dwarf material. 10 million tons, a single teaspoon. If you took a teaspoon of neutron star material and set it on the surface of the Earth, it would immediately plunge through the crust, through the mantle, through the outer core, reach the Earth's centre, and still not stop because the Earth's rock cannot support its weight. It would oscillate around the Earth's centre for a very long time, before friction eventually brought it to rest. This is not exaggerated. This is what the models predict, and the models are consistent with independent measurements from multiple observational methods. The gravitational field at the surface of a neutron star is approximately 200 billion times stronger than Earth's gravitational field, 200 billion times. If you could stand on the surface of a neutron star, which is physically impossible for reasons that will become clear, a small pebble dropped from 1 meter above the surface would strike it with the kinetic energy of several kilotons of conventional explosive. The escape velocity from the surface of a neutron star is approximately half the speed of light. Any object launched from the surface at less than half the speed of light would arc back down. A rocket capable of escaping a neutron star's gravity would need to reach half the speed of light just to get away. At the core of the neutron star, conditions may exceed anything achievable in a terrestrial particle accelerator. The density at the core is so extreme that it is genuinely unknown what the matter there consists of. Whether it remains neutrons, whether it transitions to a state of free quarks and gluons, whether exotic particles called hyperons are present, whether there is a superfluid region, multiple theoretical models exist, and they make different predictions. The observations needed to distinguish between them are technically difficult. This is an open question at the frontier of physics, and it will remain open until better instruments and better observations can provide the necessary constraints. The interior of a neutron star is one of the most extreme and least understood environments in the universe, and it exists in objects scattered by the billions through the galaxy, all around you, invisible. A neutron star carries the angular momentum of the original stellar core, conserved through the collapse. The core was rotating before it collapsed. When it collapsed from roughly Earth-size to 20 kilometers in diameter, a reduction in radius by a factor of roughly 50,000, conservation of angular momentum caused it to spin up by an enormous factor. It is the same principle as a figure skater pulling in her arms and spinning faster, except that the reduction in radius here is not a few tens of centimeters, but tens of thousands of kilometers. Some neutron stars rotate hundreds of times per second. The fastest known pulsar rotates 716 times per second. Its equator is moving at roughly a quarter of the speed of light. As a neutron star rotates, its powerful magnetic field sweeps beams of electromagnetic radiation across space. If one of these beams sweeps across the Earth, we detect a pulse of radiation each time the beam reaches us, once per rotation. We call these objects pulsars. The pulses are extraordinarily precise. The rotation rate of a pulsar is so stable that the best pulsars are competitive with atomic clocks as timekeeping instruments. Some pulsars have been measured to be more stable than atomic clocks over certain timescales. A dead star rotating hundreds of times per second, its precision, maintained by the physics of the collapse, is one of the most accurate timekeepers in the known universe. Pulsars were used to make the first confirmed detection of a planet outside our solar system. In 1992, Alexander Wolszczan and Dale Frail announced the discovery of 2 planets orbiting a pulsar designated PSR 1257+12, located approximately 2,300 light-years from Earth. The discovery was made not by seeing the planets directly, they are far too small and too far away for that, but by detecting tiny deviations in the timing of the pulsar's pulses. A planet orbiting a pulsar exerts a small gravitational tug on it, causing the pulsar to wobble slightly in its orbit. That wobble introduces tiny systematic variations in the arrival time of the pulses, variations of microseconds, measured with the precision that only a pulsar can provide. The planets were detected as disturbances in a clock. They orbit a dead star. Whether they could harbour any form of life is a question no one has come close to answering. The first pulsar was detected by Jocelyn Bell Burnell in 1967. working as a graduate student at the Mullard Radio Astronomy Observatory in Cambridge. She'd helped to build the radio telescope used for the detection, a vast array of more than 1,000 wooden poles connected by 120 miles of wire, covering 4.5 acres of Cambridge countryside. She was responsible for analysing the paper charts of data that the telescope produced, meters of them every day. She noticed a regular signal, pulses arriving every 1.337 seconds with extraordinary consistency. The team initially labelled the source LGM1, Little Green Men, genuinely uncertain whether they were receiving artificial signals from another civilization. The hypothesis was ruled out within weeks when similar signals were found from other locations in the sky. No civilization could be responsible for sources spread across different directions in the galaxy. The sources were natural. They were neutron stars, and the radio beams sweeping across Earth were the rotation signatures of stellar corpses. The Nobel Prize for the discovery of pulsars was awarded in 1974 to Anthony Hewish, Belle Burnell's supervisor. Belle Burnell herself was not included in the prize, an omission that remains one of the most discussed controversies in the history of the Nobel Prize. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics. She donated the entire prize money, approximately $3 million, to fund scholarships for underrepresented groups studying physics. The data she collected in 1967 has been cited in tens of thousands of subsequent scientific papers. Some neutron stars have magnetic fields so extreme that they represent a separate class of object. A standard neutron star has a magnetic field roughly 1 trillion times stronger than Earth's. Magnetars, a subset of neutron stars, have magnetic fields 10 to 1,000 times stronger still. At a distance of 1,000 kilometers from a magnetar, its magnetic field would be strong enough to disrupt the electron orbitals in atoms, to alter the fundamental chemistry of matter at the quantum level. A magnetar 1,000 kilometers away would be lethal not through radiation alone, but through the direct effect of its magnetic field on the molecular structure of anything within range. There are known magnetars in the galaxy. The nearest confirmed magnetar is approximately 9 light-years away. This is not a practical concern, but it is worth sitting with for a moment. This is a real object. It exists. The universe permits things like this to exist. In December of 2004, a magnetar called SGR 1806-20, located approximately 50,000 light-years from Earth on the far side of the galaxy, released a burst of energy in approximately 1/10 of a second, totaling more energy than the Sun radiates in 250,000 years. The burst reached Earth in the form of a gamma-ray flash, powerful enough to partially ionize the upper atmosphere. It was detected by multiple spacecraft simultaneously. Despite traveling 50,000 light-years to reach us, it saturated the detectors on several satellites. It was described by the astronomers who analysed the data as the brightest event from beyond our solar system ever recorded in human history. It lasted 1/10 of a second. That is what the data says. The neutron star is not the most extreme thing a stellar collapse can produce. For massive enough stars, those with initial masses above roughly 20 to 25 solar masses, though the exact threshold is uncertain and actively debated, the collapse does not stop at neutrons. The mass is so great that even neutron degeneracy pressure is overcome. The collapse continues. It does not stop. What forms is a black hole. A black hole is a region of spacetime where gravity is so intense that the escape velocity exceeds the speed of light. Nothing that crosses the boundary of this region, called the event horizon, can return. Not matter, not radiation, not any form of information, at least in the classical description. The event horizon is not a physical surface. It is not made of anything. It is a mathematical boundary, a point of no return defined entirely by the curvature of spacetime, caused by the concentrated mass within. The event horizon of a 10 solar mass black hole is approximately 60 kilometers in diameter. 60 kilometers, a distance you could drive in less than an hour on a highway. The tidal forces at the event horizon of a stellar mass black hole would stretch any ordinary object into a thin stream of particles before it reached that boundary. The difference in gravitational force between your head and your feet being fractionally closer to the singularity, being pulled fractionally harder, would increase without bound as you approached. This effect has been named spaghettification in the peer-reviewed literature. The word is used without irony. The physics is exact. What happens at the singularity, the mathematical point at the center of the black hole, where the equations predict infinite density, is genuinely unknown. General relativity, which has been tested to exquisite precision in every other context where it can be tested, breaks down at the singularity. Quantum mechanics, as currently formulated, does not describe it. The singularity is a place where the known laws of physics cease to make predictions. It is not that the physics is very complicated there. It is that physics as we understand it does not apply. This is an honest statement of the boundary of human knowledge, and it is important not to paper over it with confident language. There is an additional path in stellar death that deserves careful attention. In some binary systems, two neutron stars orbit each other. Over millions or billions of years, they gradually lose energy by radiating gravitational waves, ripples in space-time itself, and slowly spiral together. When they finally merge, the result is a kilonova, an explosion powered by entirely different physics than a supernova, producing different elements and leaving a different kind of remnant. On August 17, 2017, the LIGO and Virgo gravitational wave detectors simultaneously detected a signal from two neutron stars merging approximately 130 million light-years away. The gravitational wave signal lasted approximately 100 seconds, far longer than the fraction of a second signals from merging black holes, because neutron stars are less massive and spiral together more slowly in the final moments. Within 1.7 seconds of the gravitational wave merger, gamma-ray satellites detected a burst of high-energy radiation from the same location. Within 11 hours, optical telescopes had identified the source in a galaxy called NGC 4993. What followed over the next days and weeks confirmed something that had been theorized for decades. The merger was producing heavy elements via the R process: gold, platinum, strontium, and other elements heavier than iron. Their chemical signatures readable in the light from the explosion across 130 million light-years. Astronomers estimated that the merger produced several times the Earth's mass in pure gold alone, in the space of a fraction of a second. The periodic table was not written by one kind of stellar death. It was written by several. The gold in your ring might have been forged in a collision between two dead stars at a time when the most complex life on Earth was a single-celled organism. The shockwave of that collision only reached us in 2017. This is not speculation. This is what the data says. There are stellar deaths that do not fit neatly into any of these categories. The universe has more ways to kill a star than we have fully characterized. Very massive stars, those with initial masses of roughly 100 solar masses or more, may produce jets of ultra-energetic radiation, blasted in two narrow beams along the rotation axis as their cores collapse. These jets, when pointed toward Earth, are observed as gamma-ray bursts, the most energetic electromagnetic events in the known universe. A long gamma-ray burst lasting a few seconds can release more energy than the Sun will emit across its entire 10 billion year lifetime, beamed into a cone. Multiple independent instruments have confirmed this. The events are real, and they happen regularly in the universe. The exact mechanism of jet formation remains an area of active research. Then there are the pair instability supernovae. Stars with initial masses of roughly 130 to 250 solar masses may reach a condition in their cores where the gamma rays produced by the hot plasma have enough energy to spontaneously produce positron pairs. This pair production absorbs energy that was previously providing pressure support. The core softens, gravity takes over. But in some mass ranges, the resulting thermonuclear explosion is so powerful that it completely disrupts the entire star, leaving no remnant at all. No white dwarf, no neutron star, no black hole, just an explosion that consumes the star entirely and returns everything to the interstellar medium. Several candidate pair instability events have been identified in recent years. The analyses remain ongoing, and there is the possibility of a direct collapse to a black hole, a massive star's core collapsing so rapidly and completely that no significant explosion propagates through the outer layers. The star simply vanishes. In 2009, a massive star in a galaxy 6 million light-years away, catalogued as N6946-BH1, was observed to brighten slightly and then fade completely over the following years. No supernova had been detected. A later analysis found no trace of the star at its former location. The most likely explanation is a failed supernova. The core collapsed directly to a black hole, swallowing the outer layers without triggering an explosion. This has not been definitively confirmed, but the data is consistent with it. The universe appears to permit stars to simply disappear. These edge cases matter because they affect how we understand the history of chemical enrichment in the galaxy. A star that collapses directly to a black hole without exploding does not return its processed elements to the interstellar medium. The nucleosynthesis products are swallowed. Understanding what fraction of massive stellar deaths end in direct collapse versus explosion changes our models of how quickly and how thoroughly the universe enriched itself with heavy elements, and therefore how quickly the conditions for complex chemistry, planets, and life could have arisen. Now we have to go somewhere uncomfortable. The Sun will die too. The Sun is approximately halfway through its hydrogen-burning lifespan. In roughly 5 billion years, the hydrogen in its core will be sufficiently depleted that the core will contract and heat. The outer layers will expand, and the Sun will become a red giant. This is not in question. It is confirmed by stellar models, confirmed by observations of other stars at comparable stages, and consistent with every physical measurement we have made of the Sun's internal structure and composition through a technique called helioseismology, the study of sound waves that reverberate through the solar interior and emerge at the surface as subtle oscillations that can be measured by sensitive instruments. In approximately 5 billion years, the Sun's outer layers will expand to encompass the orbit of Mercury, then Venus, possibly Earth. The models disagree slightly on whether Earth itself will be physically engulfed. Some suggest that as the Sun loses mass through the stellar wind, Earth's orbit will migrate outwards slightly, and Earth might survive the expansion geometrically. But this is largely beside the point. Even if Earth's orbit carries it outside the expanded solar radius, the surface temperature of the Earth during this phase will be far beyond any possibility of liquid water, several hundred degrees Celsius at minimum. The oceans will have boiled away billions of years before the red giant phase even begins. The problem arrives even earlier. The Sun brightens gradually as it ages. It is roughly 30% brighter today than it was when the solar system formed, and it will continue to brighten. Within roughly 1 to 2 billion years, the increased solar luminosity will trigger a runaway greenhouse effect on Earth, rendering the surface uninhabitable long before the red giant phase begins. The oceans evaporate, the surface sterilizes. The timeline of Earth's habitability is not 5 billion years, It is more likely on the order of 1 billion years of remaining time, at most. 1 billion years sounds like a long time. The entire span of complex animal life on Earth so far is roughly 600 million years. The question of what happens to any life that might exist on Earth 1 billion years from now is obviously not a practical concern for anyone alive today. But it is worth acknowledging the structure of the problem. The habitability of Earth is not a permanent condition. It is a window, bounded on one end by the formation of the planet and on the other end by the brightening of the sun. We are somewhere inside that window. We do not know exactly where. But the window has an end, and the end is caused by the same process that created the window in the first place, the life cycle of the star at the center of the solar system. After the red giant phase, the sun will eject its outer layers as a planetary nebula. What remains will be a white dwarf, cooling over billions and billions of years. It will not explode. It will not become a neutron star. The sun is not massive enough. It will simply cool slowly into darkness. 5 billion years resists genuine comprehension. The entire history of life on Earth spans approximately 3.8 billion years. The entire age of the universe is 13.8 billion years. 5 billion years from now, the Milky Way will have merged with the Andromeda Galaxy, a collision already in progress, already producing measurable distortions in both galaxies' outer structures, expected to become dramatic in roughly 4 billion years. The night sky will be completely transformed. New stars will form from the combined gas reservoirs. The sun will have a different set of neighbours. The constellations will be unrecognizable. All of this will happen, and at the end of it, the sun will still be cooling toward darkness. This is not dread. This is just the structure of reality. The same reality that will eventually kill the sun is the reality that produced everything you have ever known. What are we learning at this moment that we did not know before? The James Webb Space Telescope, operational since 2022, is providing spectroscopic data of supernova remnants, planetary nebulae, and active transient events with a sensitivity and resolution that was not achievable with previous instruments. Analysis of SN 1987A continues. Observations of supernovae in distant galaxies are being made at redshifts that were previously inaccessible. The composition of the ejecta from these events is being read directly from the light they emit, confirming and extending our models of stellar nucleosynthesis in ways that were simply impossible before this instrument existed. The LIGO, Virgo, and KAGRA gravitational wave detector network is detecting compact object mergers at rates that allow statistical analysis. The properties of neutron stars, their masses, their radii, the stiffness of their interiors, are being constrained by gravitational wave observations in combination with X-ray and optical data. The equation of state of dense nuclear matter, the fundamental relationship between pressure and density in the core of a neutron star, is being bounded more tightly with each new merger event. The unknown interior of the neutron star is becoming slightly less unknown. The Square Kilometre Array, a radio telescope network under construction in South Africa and Australia, will be the largest radio observatory ever built when it is complete. The number of known pulsars, currently around 3,000, may increase by an order of magnitude. Pulsars in exotic configurations, orbiting black holes in triple systems, may be found for the first time, providing gravitational laboratories of unprecedented precision. And there is a particular observation that many in the field are waiting for with specific anticipation. Betelgeuse. Betelgeuse is one of the brightest stars in the night sky. It forms the left shoulder of the constellation Orion, visible to the naked eye on any clear night from most locations on Earth. It is approximately 700 light-years away. It is somewhere between 10 and 20 times the mass of the Sun. It is a red supergiant in an advanced stage of its life. Betelgeuse will undergo a core collapse supernova. This is established by its mass and its evolutionary stage. The question is when. In astronomical terms, Betelgeuse is expected to explode within the next 100,000 years. This sounds like a long time. In astronomical terms, compared to the age of the universe, it is essentially imminent. The silicon burning phase of a star like Betelgeuse lasts approximately 1 year before core collapse. If Betelgeuse were currently in its silicon burning phase, the observational signatures of those interior processes would be essentially undetectable at this distance with current instruments. We cannot see what is happening inside. We do not know if Betelgeuse is a week away from exploding or 100,000 years away. There is no instrument on Earth or in orbit that can distinguish between these two possibilities at this time. In late 2019 and early 2020, Betelgeuse dimmed noticeably, to the faintest it had been in recorded history, visible to the naked eye. Media coverage speculated about whether the explosion was imminent. The astrophysics community was more measured, and they were right to be. Subsequent analysis established that the dimming was caused by a large ejection of material from the star's surface, a cloud of cool dust that temporarily obscured the star's light, an event now called the Great Dimming. The star subsequently returned to near its normal brightness and has since brightened beyond its historical average. The Great Dimming was unusual. It was informative about how red supergiants behave in their late evolutionary stages. It was not the precursor to an explosion. The sign will come. We do not know when. When Betelgeuse explodes, it will be visible from Earth in daylight for weeks. At night, it will be bright enough to cast shadows. Every gravitational wave detector on the planet will trigger. Every neutrino detector will register thousands of particles, not 19, as with S1987A, but thousands, because Betelgeuse is far closer and the detectors are far more capable. Every telescope on the planet will pivot toward Orion. It will be the most intensively observed astronomical event in human history. The combination of instruments that exist now, James Webb, LIGO, IceCube, the global network of optical and radio telescopes, will all be pointed at the same event simultaneously, collecting data across every accessible wavelength and particle type at the same moment. The physics of core collapse will be measured with a precision that SN 1987A's 19 particles could not provide. There are physicists and astronomers alive right now who have spent their entire careers building toward this moment. Detector physicists who have spent decades making neutrino instruments more sensitive, knowing that the payoff will come in a burst of a few seconds when a nearby star collapses. Theorists who have spent careers building the simulations of core collapse, waiting for the observational data that will test their models against reality. Observers who have catalogued Betelgeuse for years, measuring its brightness and spectrum and surface structure, building the baseline that will allow the explosion, when it comes, to be understood against the long history of what was there before. All of them are waiting for the same event. None of them knows when it will arrive. Some of them will spend their entire careers waiting and never see it. Some of them may see it tomorrow. We do not know if it will happen in a human lifetime. We do not know if it will happen in 1,000 lifetimes. We are watching. When you look up at the night sky, you're looking at stars that are, by and large, alive. They're burning. They are in hydrostatic equilibrium. They will live for millions or billions of years before anything changes. The night sky feels static. It has looked essentially the same for the entire span of human civilization. But the galaxy is full of dead stars that you cannot see. White dwarfs are faint. The nearest known white dwarf, Sirius B, is the companion to Sirius, the brightest star in the night sky, and it is invisible to the naked eye, despite being only about 8.6 light-years away. Neutron stars are tiny and usually dark, except when they are pulsars pointing a beam at us, or when they are accreting material and emitting X-rays. Black holes emit nothing on their own. They are detectable only through their gravitational effects on surrounding matter or through the gravitational waves they produce during mergers. There are estimated to be approximately 1 billion neutron stars in the Milky Way galaxy. 1 billion compact stellar corpses, each roughly 20 kilometers in diameter, each containing more than a solar mass of matter, distributed through a galaxy 100,000 light-years across. Most of them are cold, dark and silent. The pulsars we detect are a small fraction of the total. We only detect the ones whose beams happen to sweep across Earth. The majority of neutron stars are simply there, invisible, drifting. The number of stellar mass black holes in the galaxy is estimated at roughly 10 million to 1 billion, depending on the assumptions in the model. Most of these are solitary and undetectable. The ones we have identified are almost entirely those in binary systems, where material from a companion star falls onto the black hole and emits X-rays in the process. The black holes themselves are dark. The nearest known black hole to Earth was identified in 2022 using data from the Gaia Space Observatory, which has been measuring the precise positions and motions of billions of stars with unprecedented accuracy. The Discovery team found a star in the constellation Ophiuchus moving in a way consistent with orbiting an invisible companion approximately 10 times the mass of the Sun. The companion is a black hole. It is approximately 1,560 light-years from Earth. It is dormant, not accreting material, not emitting X-rays. Simply there, orbiting another star, invisible, as it has been for however many millions of years since it formed. 1,560 light-years. At the speed of the New Horizons probe, currently the fastest human-made object to leave the solar system, it would take approximately 30 million years to reach it. The nearest black hole is not a practical concern, but its existence, confirmed by the data, is a reminder that the stellar graveyard is not distant. It is all around us. We simply cannot see it. The catalogue of dead stars grows with every generation of instruments. When LIGO detected its first gravitational wave signal in September of 2015, two merging black holes 1.3 billion light-years away, their collision producing a ripple in space-time that shifted the mirrors of the detector by less than 1,000th the diameter of a proton. It opened an entirely new observational window on the universe. Before that detection, everything we knew about the cosmos had been learned from electromagnetic radiation, light, radio waves, X-rays, gamma rays. After that detection, we could also hear the universe. The gravitational wave signal from those two black holes, converted into sound for the press conference, lasted about 1/5 of a second and produced a characteristic rising chirp as the black holes spiraled together in their final moments. That 1/5 of a second of sound contained more information about the behavior of matter at extreme densities than decades of theoretical work had been able to provide. It was measured directly. It is confirmed. Every compact object merger detected since has added to that catalogue. The dead stars are not just relics of the past, they are active participants in the present-day universe, merging, radiating, accreting, lighting up the sky in X-rays, producing the heaviest elements in the periodic table. The stellar graveyard is not quiet. It is full of the most energetic, ongoing events in the observable universe. The universe is approximately 13.8 billion years old. For the first several hundred million years, there were no elements heavier than hydrogen, helium, and trace amounts of lithium. The first stars, enormous, short-lived objects, formed from this primordial gas, containing no heavy elements and likely reaching masses hundreds of times that of the Sun, burned through their fuel in millions of years and exploded or collapsed, seeding the universe with the first carbon, the first oxygen, the first iron. These were the original stellar deaths, and they set in motion the chemical enrichment that would eventually make planets and life and this moment possible. We have not directly observed one of these first-generation stars. They are gone. Their deaths happened before the first galaxies fully formed, and the light from those events has been stretched by the expansion of the universe into the infrared, diluted by distance and time. The James Webb Space Telescope is beginning to probe these early epochs, detecting galaxies existing within a few 100 million years of the Big Bang that are already chemically complex, already containing significant quantities of heavy elements. This implies that the first generation of stars lived and died even faster than earlier models suggested. The early universe was a more violent and more rapidly evolving place than many expected. The data is being incorporated, the models are being adjusted. Every star that has ever exhausted its fuel has left something behind: a white dwarf, a neutron star, or a black hole, or has scattered its material back into the interstellar medium. The interstellar medium today is not the same composition it was when the galaxy formed. It has been enriched, generation by generation, by the products of stellar nucleosynthesis. Each cycle of star formation and stellar death adds heavier elements to the available pool. The universe started as hydrogen and helium. Everything else, every element above helium on the periodic table, was made in stars. The universe gets chemically richer over time because stars die. The sun was formed from a cloud of gas and dust that was already chemically enriched by multiple previous generations of stars. The Earth formed from material in that same cloud. Life formed from material on the Earth. The enrichment process that made complex chemistry possible, that made organic molecules possible, that made the diversity of biochemistry possible, that made you possible, required billions of years of stars living and dying before the sun ever ignited. We are late in a very long process. We are the products of generations of stellar death. There is something exact and strange about this that is worth stating plainly, without decoration. The iron in your blood is carrying oxygen through your veins. At this moment, using the same physics that governs the collapse of stellar cores. The carbon atoms forming the backbone of your DNA were fused in the triple alpha process inside a red giant that died long before the Earth existed. The calcium in your bones was scattered across space by a supernova shockwave. The gold in any piece of jewelry near you was forged in the collision of two neutron stars and dispersed across space over millions of years before being swept up into the cloud that became the solar system. You are not like the stars in some vague poetic sense. You are made of the physical products of stellar death, assembled by chemistry and time into something that can ask where it came from. The universe is strange and large. The forces that govern it do not care about any particular arrangement of atoms. Stars live and die by physics, not by intention. The explosions that made you possible killed whatever was nearby. The processes are indifferent in the sense that physical law has no preference. It does not distinguish between a gram of iron in a stellar core and a gram of iron in a human heart. The same physics applies to both. The same equations, the same constants, the same universe. And yet here we are, asking the question. There is one more thing worth saying about the scale of what we have been describing. The universe contains, by current estimates, roughly 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Most of those stars have already died, or will die in a future so long that the numbers involved become meaningless. The total number of stellar deaths that have occurred since the universe began, the total number of explosions, collapses, white dwarfs formed, neutron stars spun up, black holes created, neutron star mergers completed, is a number far beyond any intuitive grasp. Each one of those deaths scattered material into space. Each one contributed to the chemical enrichment of a corner of the universe. The scale of the process that made you is not the scale of a planet or a solar system or even a galaxy. It is the scale of the observable universe, operating across 13.8 billion years. The elements in your body have been through stellar interiors. They have been in the cores of dying stars. They have been scattered by explosions and pulled together by gravity and processed again and scattered again across timescales that make human history look like a rounding error. The iron that is carrying oxygen through your blood right now may have been inside the cores of multiple different stars across its history, forged and expelled and gathered and processed again. We cannot trace the exact path of any individual atom, but we know the class of events that must have occurred. We know the physics, we know the time scales, we know the composition of the universe at the beginning and the composition now. We can reconstruct the broad history, even if the specific biography of any given iron atom is lost. The investigation into stellar death is not finished. The questions that remain: what happens at the singularity? What is the true composition of a neutron star's core? What determines the exact dynamics of a supernova explosion? Where the precise threshold lies for a collapsing star to form a black hole rather than a neutron star? What determines whether a massive star dies with a roar that lights up a galaxy or with a silence that leaves no trace are not small questions. They are questions at the boundary of physics as it currently exists. Answering them will require new instruments, new mathematics, new theoretical frameworks that may not yet exist. There is a particular aspect of this boundary worth sitting with. The interior of a neutron star is one of the few places in the universe where multiple fundamental forces operate simultaneously at extreme conditions: gravity, the strong nuclear force, the weak nuclear force, quantum mechanics. It is, in a sense, a natural laboratory for physics that no human-built machine can replicate. And it is surrounded by a crust and an atmosphere and a neighborhood of magnetic field, and we can only read its interior from the outside, through the timing of pulses, or the spectrum of X-rays, or the shape of a gravitational wave. We are trying to understand the most extreme matter in the universe, the way a doctor tries to understand the human body from the outside, with instruments held against the skin. We are making remarkable progress. We are still far from complete. The instruments are improving, the simulations are becoming more detailed, the theoretical models are being confronted with better data than ever before. Every time a massive star collapses somewhere in the observable universe, we have slightly better tools to observe it than we had before. Every neutron star merger detected adds a data point to our understanding of what dense nuclear matter actually does. Every precisely timed pulsar measurement constrains the interior structure of neutron stars in ways that no laboratory experiment can match. Somewhere in the galaxy, at this moment, a massive star is in one of the late burning phases. Its surface is unchanged, bloated and red, giving no indication of what is happening at its core. Inside, silicon is becoming iron. The fuel is running out. The balance between gravity and pressure is approaching its final hour. The star does not know this is ending. It has no knowledge of what is coming. The physics will proceed as it has always proceeded, indifferent, precise, extraordinary. And somewhere on this planet, circling a middle-aged star that has 5 billion years left, made entirely of material that dead stars discarded, people are building instruments to watch the next one. Detector physicists are making neutrino instruments more sensitive. Gravitational wave engineers are reducing noise floors. Theorists are running simulations of stellar collapse on the largest computers available, trying to capture the three-dimensional turbulence and convection that determines whether the shockwave revives or stalls. Observers are cataloguing every massive star within reach, building the baselines that will make the next nearby supernova, whenever it comes, the most thoroughly documented event in the history of science. The iron in your blood is waiting. The universe is patient. The physics is precise. The dead stars are everywhere around you, invisible and drifting, scattered through a galaxy that has been recycling stellar material for 10 billion years. You are the current state of some of that material. You are temporary, as everything is temporary at stellar timescales. But you are here, and you are made of the right elements, assembled in the right configuration, in the right window of time, on the right kind of planet, around the right kind of star. The chain of stellar deaths that produce the atoms in your body stretches back to the first stars that ever formed, and it will continue forward through the deaths of stars not yet born, long after the sun has cooled to darkness. The investigation is ongoing. We are the species doing it. Right now, without your knowledge or consent, the iron in your blood was forged inside a dying star. Not metaphorically, not as a poetic approximation. The iron atoms currently carrying oxygen through your body were created in the final seconds of a stellar explosion so violent it briefly outshone every other star in its galaxy combined. That event happened billions of years before the Earth existed, and here you are, walking around with the remnants of it in your veins. You feel nothing. Your hand rests where it rests. The room around you is quiet. Nothing about the ordinary physics of this moment suggests that you are, in a very literal sense, the recycled material of dead stars. But you are. And the process that made you possible, the death of stars, is one of the most extreme and poorly understood sequences of events in all of known physics. This is confirmed science. This is not speculation. The data has been collected, peer-reviewed, published, and replicated by independent teams across multiple decades. What happens when a star dies is real, and it is stranger than almost anything else in the universe. If this is the kind of investigation that interests you, subscribe now. The investigation begins here. Consider what it means to hold the remnant of a stellar explosion in your hand, not in a museum, behind glass, in your own hand, right now. If you press your palm flat and look at the lines running across it, the lines that palmists have been misreading for centuries, the iron that gives your blood its colour is cycling through the capillaries beneath that skin at this moment. That iron was not made on Earth. It was not made in any process that has ever occurred on Earth or could occur on Earth. It was made in a nuclear explosion larger than anything the planet has ever experienced, in the core of a star that no longer exists, in a galaxy that may or may not still look the way it looked when that star died. And then it drifted through space for billions of years, mixed into a cloud, collapsed into a solar system, settled into a planet, dissolved into an ocean, found its way into a living cell, and eventually became part of you. This chain of events is not a metaphor for connection. It is the literal causal chain. It is the documented sequence of events. And it began with a death. For most of human history, the stars were eternal. That was not merely the intuition of uneducated people staring at the night sky. It was the formal intellectual consensus held by some of the most careful and rigorous thinkers in human civilization across many centuries and many cultures. The stars did not change. They were the fixed backdrop against which everything mortal played out. The ancient Greek philosophers, whose cosmological frameworks shaped Western thought for nearly 2,000 years, placed the stars in a realm of perfection and permanence beyond the moon. Change in their model was a property of the sublunar world, the messy, corruptible, temporal realm of earth, water, air, and fire. Above the moon, things were eternal and perfect, composed of a fifth element called ether that was immune to corruption or transformation. This was not a casual belief. It was a load-bearing pillar of the entire philosophical and theological structure of Western civilization for over a millennium. This belief was so deeply embedded that even when change in the heavens was directly observed, it was rationalized away rather than accepted as evidence against the framework. When Chinese astronomers in 1054 CE recorded a new star appearing in the constellation Taurus, bright enough to cast distinct shadows at night, visible in full daylight for 23 consecutive days, and bright enough for naked eye observation for nearly 2 years before it finally faded. The event was recorded with a remarkable precision and then absorbed without challenging the underlying cosmological order. The star faded, life continued. The view began to crack in November of 1572 when a young Danish astronomer named Tycho Brahe stepped out of his uncle's alchemy laboratory one evening and looked up at a familiar sky and saw something wrong with it. There was a star in Cassiopeia that had not been there the night before. Brahe was an experienced observer. He knew the sky. He knew this star had not been there. He called over people nearby, farmhands, servants, passers-by, and asked them if they could see what he was seeing. They could. The star was real. It was extraordinarily bright. At its peak, it was comparable in brightness to Venus at its maximum, and it remained visible in daylight for about 2 weeks. Brahe observed it with the most precise instruments available to him, attempting to measure its parallax, the slight apparent shift in position of a nearby object relative to more distant ones, caused by the observer's movement. He found none. No parallax at all, which meant the new star was extremely distant, far beyond the orbit of any planet, in the realm the ancients had reserved for the eternal and unchanging. And it was changing. It was new. And then, over months, it faded. Brahe published his observations in a book titled De Nova Stella, On the New Star. The name he used, Nova Stella, is the origin of our modern word, nova. What Brahe actually observed was not a nova in the modern technical sense. Based on the historical records of its brightness and the characteristic pattern of its rising and fading over about 16 months of total visibility, it was almost certainly a Type 1a supernova, the complete thermonuclear annihilation of a white dwarf that had accreted past its physical limit and detonated. Brahe had no framework for any of this. What he understood was that the sky had changed, and that the framework everyone had been using to understand the sky was therefore wrong in some fundamental way. He could not say what the correct framework was, but something had to give. It took another 350 years before anyone understood why. The understanding of stellar death is a recent achievement, not recent in the sense of years, but in the sense of generations. The core physical picture we have today was assembled across the 20th century, with major pieces falling into place in the 1930s, 1950s, 1960s, and continuing to develop right up to the present. The discovery of nuclear physics was required before anyone could understand what stars were actually doing. Before that discovery, the energy source of stars was a genuine, unresolved scientific mystery. In the late 19th century, the physicist William Thomson, Lord Kelvin, and the geologist Hermann von Helmholtz independently calculated how long the sun could shine if it were powered by the only mechanism the physics of the era could account for: gravitational contraction, the slow shrinking of the sun under its own weight. This mechanism is real. The problem is that it produces a maximum solar lifetime of only about 20 to 40 million years. By the late 19th century, geologists had accumulated evidence suggesting the Earth was hundreds of millions of years old, possibly older. The biologists had evidence from evolutionary theory suggesting comparable timescales for the development of life. The numbers did not add up. Something was wrong. The wrong answer was held, at the time, by some of the best physicists in the world. The deeper issue was that the physicists did not know what they did not know. They had no framework for nuclear forces. The nucleus of the atom had not yet been discovered. The neutron would not be discovered until 1932. Einstein's relationship between mass and energy had been published in 1905, but its implications for stellar physics would not be worked out for another 3 decades. The history of our understanding of stellar death is a history of having no idea what was happening, and then slowly, painstakingly, building the framework to understand it. Every major piece of the picture required a discovery that had not yet been made. Every major piece of the picture, once it was made, turned out to be more extreme than expected. The resolution came in the 20th century with the development of nuclear physics and the understanding of Einstein's relationship between mass and energy. By the late 1930s, physicists including Hans Bethe and Carl Friedrich von Weizsäcker had independently worked out the nuclear reactions powering the Sun, the proton-proton chain by which hydrogen nuclei fuse into helium, with a tiny fraction of mass converted into energy, according to the relationship Einstein described. Bethe published the definitive treatment of this in 1939 and received the Nobel Prize for it in 1967. The energy source of the stars was, for the first time in human history, understood. With that understanding came the ability to ask, what happens when the energy source runs out? In the same decade, Subrahmanyan Chandrasekhar worked out what happens to stars like the Sun after they die, and Robert Oppenheimer published papers with his collaborators arguing that sufficiently massive collapsed stars could produce what we now call black holes, though that term would not be coined for another 3 decades. The foundations of our understanding of stellar death were laid in a single decade by people working in different countries under the shadow of a world war. The physics of dying stars was worked out against the backdrop of profound human violence. This is not incidental. The physicists who understood stellar death were the same generation that built nuclear weapons, because both depend on the same underlying physics. The bomb and the star run on the same principles. The scale and the context are different. The equations are cousins. A star is not a thing that burns. That distinction matters, and it matters more than most people realize. When you burn something, wood, paper, fuel, you're running a chemical reaction. Electrons are swapping partners between atoms. Energy is released in the form of heat and light. It is fast, relatively speaking, and it consumes whatever you put into it in minutes or hours. A candle burning through the night is a chemical process, a shuffling of electrons between carbon and hydrogen and oxygen atoms. A star does something fundamentally different. A star runs nuclear fusion. Inside the core of a star, atoms are not swapping electrons. They are being crushed together with such force that their nuclei, the dense, positively charged centers of atoms, are forced to merge. Hydrogen nuclei fuse into helium nuclei. The mass of the helium that comes out is fractionally less than the mass of the hydrogen that went in. That missing mass is converted directly into energy. Because the speed of light is an enormous number, even a tiny decrease in mass produces an enormous amount of energy. This is not an approximation. This is what the equation says, and the equation has been confirmed in every context where it has been tested. To give that a number, a single kilogram of hydrogen undergoing nuclear fusion releases approximately 600 trillion joules of energy. A kilogram of coal burning releases about 30 million joules. Nuclear fusion is, per unit of fuel, roughly 20 million times more energetic than burning. That is not a rounding difference. That is a different category of phenomenon entirely. The Sun has been running this process for approximately 4.6 billion years. It will run it for another 5 billion years before the fuel situation changes enough to matter. In human terms, this timescale is incomprehensible. 4.6 billion years before today, the universe was about 9 billion years old. Complex multicellular life did not exist anywhere on Earth. There were no fish, no plants, no dinosaurs, no mammals, just single-celled organisms in an ancient ocean. The Sun has been burning since before any of that. In astronomical terms, this timescale is perfectly ordinary. Stars live on nuclear timescales, not chemical ones. And when they die on nuclear timescales too. But to understand how a star dies, you first have to understand what keeps it alive. A star is a balancing act between two opposing forces, and the balance is more precise and more dynamic than the word balance usually implies. On one side, there is gravity. The star is made of gas, predominantly hydrogen, with about a quarter helium, and all of that gas is pulling inward on itself. Every gram of gas in the star is gravitationally attracted to every other gram. Left to its own devices, gravity would collapse a star into a point. This is what gravity wants to do. It is the direction every star is always being pushed by its own mass. On the other side, there is pressure. The nuclear fusion happening in the core releases enormous amounts of energy, and that energy pushes outward. It heats the surrounding gas, which expands. It creates radiation pressure, the literal pressure of light pushing against matter. This outward push from the core exactly balances the inward pull of gravity. The star holds its shape because these two forces cancel each other out at every layer simultaneously, not just at the surface, but throughout the entire volume of the star. Astronomers call this balance hydrostatic equilibrium. It is not a static condition, like a rock sitting on a table. It is an ongoing, active, continuous negotiation between gravity and pressure, happening at every moment, sustained entirely by the nuclear burning in the core. The moment that burning changes, the balance shifts, and the burning always changes, eventually. Because fusion consumes fuel, hydrogen becomes helium, and helium, once it accumulates in the core, is not immediately usable as fuel in the same way. The temperature required to fuse helium is much higher than the temperature required to fuse hydrogen, and the core is not yet hot enough, so the helium builds up at the center of the star, while hydrogen continues to burn in a shell surrounding it. The core is now made of helium that is not burning. It is not generating energy, it is just sitting there, dense and inert, under enormous gravitational pressure. The core, without nuclear pressure to support it, begins to contract under gravity. This contraction heats the core. Compressing any gas heats it, for the same reason that a bicycle pump gets warm when you compress air. The heating of the contracting helium core heats the surrounding hydrogen shell, making it burn faster. The outer layers of the star, responding to this increased energy from the shell, begin to expand. The star grows, not slightly, dramatically. A star the size of the Sun, when it reaches this phase, will expand until its outer edge extends beyond the current orbit of Mars. The surface temperature drops as the star expands, because the same amount of energy is now spread over a vastly larger surface area. The color shifts from yellow-white to orange to red. The star becomes what astronomers call a red giant. It has not begun to die yet, but it has entered the phase of its life where death has become the destination. Inside the red giant, the contracted helium core has been heating up under gravitational pressure. When the core temperature reaches approximately 100 million Kelvin, about 7 times the current temperature at the Sun's core, which fuses hydrogen at around 15 million Kelvin, something new happens. The helium nuclei, now hot enough and dense enough, begin to fuse. 2 helium nuclei fuse to form beryllium-8, which is unstable and would normally decay almost immediately, in approximately 10 to the power of minus 16 seconds. That is 0.000000000000000000001 seconds. This decay happens so fast that beryllium-8 never accumulates in any significant quantity under ordinary circumstances. But in the dense stellar core, before the beryllium-8 can decay, a third helium nucleus strikes it. The result is carbon-12, a stable and useful nucleus. This process is called the triple alpha process because it involves 3 helium nuclei, which are also called alpha particles. And it is how all the carbon in the universe was created, including every carbon atom in your body. The triple alpha process requires not just extraordinary physical conditions, but a specific coincidence of nuclear physics that is not guaranteed by any fundamental law. The energy of the beryllium-8 plus the incoming helium nucleus has to match an excited energy state of carbon-12 very closely for the reaction to proceed at the rate needed to produce significant carbon. If the energy levels did not match, the reaction would not work. Carbon would not form in significant quantities. And if carbon did not form in stellar interiors, the universe would have very little carbon to work with when building planets and chemistry and life. In 1954, the astrophysicist Fred Hoyle predicted that this matching energy level had to exist, based on a startling line of reasoning. He was made of carbon, and carbon therefore had to be producible in sufficient quantities, and the nuclear physics therefore had to permit it, and so the energy level had to be there. He reasoned from his own existence to a constraint on nuclear physics. The specific energy level he predicted, now called the Hoyle state, was confirmed in laboratory experiments shortly after the prediction was made. It is real. It was there exactly where he said it had to be. The universe produces carbon because the nuclear physics of helium fusion happens to be tuned in exactly the right way for this to work. This is confirmed science. This is not speculation. With helium burning, the star stabilizes again temporarily. But helium is a less efficient fuel than hydrogen, and the star burns through it much faster. When the helium is exhausted, the process repeats. The core contracts, heats up. The outer layers respond. What happens next depends entirely on how massive the star is. This is the branching point. This is where the story of stellar death splits into paths that lead to radically different endings. Mass determines everything. It determines how many times the star can reignite the core with a new fuel source. It determines how violent the final moments will be. It determines what, if anything, remains after the star is gone. When a star like the Sun exhausts its nuclear fuel, it does not explode. This is one of the most common misconceptions about stellar death. The image that most people carry, the star detonating, the cataclysm, the shockwave, applies to a specific category of stellar deaths. But for the majority of stars in the galaxy, including the Sun, the end is quieter than that. It is not peaceful, exactly, but it is not an explosion. What happens instead is a gradual dispersal. The star, now a bloated red giant with its outer layers extending far into space, has been steadily losing mass from its surface for millions of years. The radiation pressure from the core drives a stellar wind, a continuous outflow of gas from the surface, similar to the solar wind that flows from the Sun today, but dramatically more intense in the red giant phase. For a star like the Sun, this mass loss amounts to billions of tons of gas escaping into space every second during the red giant phase. Over thousands of years, this strips away the star's outer layers one by one. As the outer layers are expelled, they form a shell of gas expanding outward into the space around the star. This shell glows. It glows because the stripped core beneath it, now very hot and compact, emits intense ultraviolet radiation that excites the atoms in the surrounding gas, causing them to emit light at specific wavelengths. The result is an object that, when viewed through a telescope, resembles a glowing ring or sphere of coloured light surrounding a tiny bright point. Astronomers in the 18th century, looking through the relatively modest telescopes of their era, saw these objects and mistook them for planets. They named them planetary nebulae. The name is wrong. They have nothing to do with planets, but it stuck, and we still use it today. The Helix Nebula, the Ring Nebula, the Cat's Eye Nebula, the Butterfly Nebula. These are among the most photographed objects in the history of astronomy, precisely because they are visually extraordinary. Shells of glowing gas in intricate, layered structures, often spanning many light years from edge to edge, surrounding a tiny bright point at the center. Each one of them is the death of a star like the Sun, preserved in the act of happening. The material expanding outward from those central white points has been in transit for thousands of years. The Helix nebula's gas is moving outward at approximately 31 kilometers per second and has been doing so for roughly 10,000 years. It will continue expanding for thousands more, thinning as it goes until it is too diffuse to distinguish from the general interstellar medium. A planetary nebula is a dying star's last exhalation. The material that made up the outer layers, hydrogen, helium, and the carbon and nitrogen and oxygen that the star processed over its lifetime, is being returned to the interstellar medium, the diffuse gas and dust that fills the space between stars. It is not lost, it is redistributed. It will drift in space, cooling and mixing with other clouds of gas and dust, until gravity pulls some of it together again into a new star. The material is recycled. This is not a poetic description. It is a literal description of an actual physical process that has been operating in galaxies for billions of years. What remains after the planetary nebula is ejected is the stripped core. This core is composed primarily of carbon and oxygen, the ash of helium burning. It is roughly the size of the Earth, but it contains roughly half the mass of the original star. Think about what that means. Take half the mass of the Sun and compress it into a sphere the size of the Earth. A teaspoon of its material would weigh approximately 5 tons on the surface of the Earth. Not 5 grams, 5 tons. It is a teaspoon of matter compressed far beyond anything in ordinary human experience. This object is called a white dwarf. The white dwarf does not generate energy through fusion. Fusion has stopped. There is no more fuel. It is a stellar corpse, but it is an extraordinarily hot corpse. The temperatures at the surface of a newly formed white dwarf can reach 100,000 Kelvin or more, far hotter than the surface of the Sun. It radiates this stored thermal energy into space, like a slowly cooling ember. It will continue to do so for billions of years. What prevents the white dwarf from collapsing further under its own gravity? Not fusion, not pressure from nuclear burning. Instead, it is supported by a quantum mechanical effect called electron degeneracy pressure. This is something quite different from thermal pressure. It arises because electrons, being particles of a type called fermions, cannot occupy the same quantum state simultaneously. When matter is compressed to the point where the electrons are packed tightly together, the Pauli exclusion principle, a fundamental law of quantum mechanics, resists further compression regardless of temperature. The electrons cannot be pushed any closer together without violating the laws of quantum mechanics, and so they push back. A white dwarf is held up not by heat, not by burning, but by the quantum nature of electrons. The universe at this scale is governed by quantum rules, not by the thermal ones we are familiar with from everyday life. The white dwarf will cool over time. As it cools, its surface temperature will drop, its colour shifting from white to yellow to orange to red over billions of years. Eventually, if left undisturbed, it will become a black dwarf, a cold, dark, inert sphere of carbon and oxygen floating silently in space. Here is something important. The universe is not old enough yet for any black dwarfs to exist. The oldest white dwarfs in the Milky Way are still thousands of Kelvin at their surfaces. Every white dwarf that has ever formed is still glowing. They are out there in the billions, slowly cooling, waiting for a universe old enough to finish the process. That universe is an unimaginably long time away, longer than the current age of the universe by many orders of magnitude. It is worth holding that fact for a moment. The universe is 13.8 billion years old. And yet every white dwarf that has ever formed, the first ones that appeared when the earliest generations of stars died billions of years into cosmic history, is still radiating heat. None of them have finished cooling. The universe has not had time. The process of a white dwarf cooling to a black dwarf takes so long that the universe, as it currently exists, is only in the very early stages of that process. for its oldest members. We are living in a young universe. Despite its apparent age, the black dwarfs are waiting for a future that is still unimaginably distant. But not every white dwarf is left undisturbed. Some white dwarfs exist in binary systems, paired with another star, orbiting each other across millennia, bound by mutual gravity. In these systems, if the companion star evolves and expands into a red giant, the outer layers of the companion can be pulled by gravity toward the white dwarf. This process of material flowing from one star to another is called accretion. It adds mass to the white dwarf slowly and steadily over time. The white dwarf has a limit. This limit was calculated in 1930 by a young Indian physicist named Subrahmanyan Chandrasekhar, travelling by ship from India to England to begin his graduate studies at Cambridge. He was 19 years old. During the 3-week voyage, working through the equations in a notebook, he arrived at a result that disturbed him. There is a maximum mass that a white dwarf can have and still be supported by electron degeneracy pressure. Beyond approximately 1.4 times the mass of the Sun, a threshold now called the Chandrasekhar limit, the electron degeneracy pressure is insufficient to hold up the star. Gravity wins. Something catastrophic must happen. The equations were clear. The physics was unambiguous. Chandrasekhar's result was initially dismissed by Arthur Eddington, one of the most respected figures in astrophysics at the time. Eddington argued publicly and emphatically that nature would not permit such an outcome. He said the result was physically absurd. He used his considerable institutional prestige to marginalize Chandrasekhar's calculation. He was wrong. Chandrasekhar was right. This is now established beyond any reasonable doubt. Chandrasekhar received the Nobel Prize in Physics in 1983, more than 50 years after his calculation on that ship. The gap between derivation and recognition is itself a lesson in how the scientific community sometimes responds to results it finds uncomfortable. When a white dwarf accretes enough mass to reach or exceed the Chandrasekhar limit, what follows takes approximately 1 second. Nuclear fusion ignites throughout the entire body of the white dwarf simultaneously, in a runaway thermonuclear reaction that consumes the entire star. The energy released is equivalent to roughly 1 to 2 times 10 to the power of 44 joules. The star is completely destroyed. Nothing remains. This event is called a Type 1a supernova, and it releases more energy in that 1 second than the Sun will radiate across its entire 10 billion year lifespan. Because Type 1a supernova are always triggered by the same physical threshold, the Chandrasekhar limit, they always produce roughly the same peak brightness. Astronomers call them standard candles. By measuring how bright a Type 1a supernova appears from Earth and comparing it to how bright it must actually be, they can calculate the distance to it with a remarkable precision. This is the same logic as knowing that all 100-watt light bulbs produce the same amount of light. If one looks dimmer than another, it must be farther away. The exact ratio of brightness tells you exactly how much farther. It was this method applied to Type 1a supernovae in distant galaxies in the late 1990s that produced one of the most unexpected results in the history of science. 2 independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were each measuring how quickly the universe's expansion was slowing down. Based on all the dominant theoretical models, the expansion was expected to be decelerating. The mutual gravitational attraction of all the matter in the universe should be pulling everything back, slowing the outward motion that began with the Big Bang. The data from the supernovae told a completely different story. The distant supernovae were consistently dimmer than expected, not slightly. Measurably, consistently, statistically significantly dimmer, meaning they were farther away than the redshift of their host galaxies predicted. The universe was not slowing down, its expansion was accelerating. Something is pushing the universe apart with increasing force. That something has been named dark energy. It accounts for